So let's expand on what we already know. We know that from remainder theorem, if I have a value here and that goes to 0, that means there's no remainder, right? I know that that value now, a, could be x equals to a, bring it over, x minus a is now a factor. But what I just learned in the last question was to look at that last number. Remember that last number was minus 12? And I found out that all of my factors multiplied together. Once I factored this thing, once I got it down to the binomials, and I just took the numbers and I multiplied the numbers all out, the numbers worked out to be minus 12. Knowing this is powerful because that, ladies and gentlemen, is called the integral zero theorem. So what does this mean? Watch. If the polynomial, okay, has factors of this form, you know and I know that a is a factor of the constant term. What does that mean? You know that a here? Remember that a value that we figured out in the last question? That actually was a factor of minus 12. That was a 1. The other one was, I think, a 2. And the other thing, I think, was a 6. Every one of these was a factor of minus 12. That's what this statement is saying. So what does this mean? This implies then that if we looked at the factors of the constant term here, we could find potential factors of the original polynomial. No. Yes. The zeros of the polynomial must, whatever the zeros are, they must be factors of constant term. And that's why they call them integral zeros. That's why this is called the integral zero theorem. So how do you go about doing this then? Let me show you. This is just going to boggle your mind. It is so cool. So if you're factoring a higher degree polynomial, what do? First is you determine what are the integral factors. Look at the constant term. Tell me all of the factors for the constant term. In this case, I've got 12 here. These are potential zeros. Now, notice how I said potential zeros. Well, wait a second. How do you know if they're real zeros or not? Well, that's where the integral theorem comes in. You're going to use the actual factors are going to be done by, guess what? The factor theorem and the remainder theorem. So what you're going to do, watch this, it's really, really simple. And then after that, you can use things like synthetic division, factoring trinomials, and then you can completely factor. Look at this god-awful question that I gave you. Oh my God, it's degree 4. No. You're probably saying, oh, you can't do this. Yes, you can, because watch. I'm going to use this idea back here of the integral zero theorem. I'm going to go right to this guy right here. I'm going to look at all the potential factors of this. That's what question part A tells you. It says, develop me a list of potential factors, potentials which become potential zeros. Okay, so give me all of the factors of 12. Well, gosh, of course, plus or minus 1. I mean, 1 is going to be a factor, right? And it seems that 1's going to be a factor of every single one of these questions. So always try with 1. 1 is the simplest number to work with. Check this out. Try plus or minus 2. That divides into 12. Plus or minus 3 divides into 12. Plus or minus 4 divides into 12. Plus or minus 6 divides nicely into 12. And then now plus or minus 12. So this is a list. Look at this. You have 2, 4, 6, 8, 10, 12 potential factors that you got to figure out. Oh boy, that's going to be a pain in the butt. No, it's not. Watch how easy this is. I'm going to just go out and I'm going to start trying them right now. I'm going to try P of 1. Let's try it right now. P of 1. Okay, here we go. So throw these values into the original polynomial and see if it actually works. Remember, that's our factor theorem and our remainder theorem. Okay, here we go. Boom. So we're going to go 1 to the power of 4 plus 2, 1 cubed, minus 7 times 1 squared, minus 8 times 1 plus 12. Got it? Okay. 1 to the power of 4, 1. 1 cubed is 1 times 2, 2. 1 squared is 1 minus 7. Look how easy this is. Minus 8 plus 12. Okay, perfect. Let's figure this out. Minus 7 minus 8, that's of course minus 15. 12, 2, 14, 15. Oh my goodness, plus 15. We found it on the first shot. We found out that this gives us no remainder, which means x equals to 1. Great, that's what we'd use in synthetic division, but the actual factor, you have to bring it over onto the other side. There's your first factor. So I wonder, knowing this now, what is left after we divide this out using synthetic division? Well, now that I know that 1 works, I'm going to get rid of all this. I'm going to do that on scrap, okay? And I'm going to just pop it in there. Let's see. 1 is this, okay. Synthetically divide 1, 2, minus 7, minus 8, and 12. I better get 0 down here or I did something wrong. Okay, here we go. 1 times 1 is 1. That's 3. 3 times 1 is 3. Okay, that's minus 4. Minus 4 times 1 is minus 4. That's going to give us minus 12. Minus 12 times 1 is 12. Oh, look at that. It worked. Okay, 1's position, x squared position, x cubed position. So guess what? You're now dealing with an x cubed function. Okay, so guess what? You got to do this all over again so that you can figure out which one, in fact, is going to work. Okay, well, wait a second. We've tried positive 1. The other factor here was plus or minus 2. Let's try positive 2. Let's see if it works. Now, am I going to go back to the original? Heck no. I'm going to start dealing with the simpler one. Why? Because if it's a factor of the simpler one, it has to be a factor of the larger expression. Okay, so I'm going to try positive 2 and see if it works. Okay, so here we go. P at 2. Punch it in there. 2 to the power of 4. I'm just going back to here. 2 to the power of 4 plus 2 times 2 cubed minus 7 times 2 squared minus 8 times 2 plus 12. And you know, honestly, you can punch this into your calculator. That's going to help you just huge. 2 to the power of 4. Okay, 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay. Plus 2 cubed, 2 times 2 times 2 is 8 times 2 is, oh, look at that. That's 16 as well. Okay, now you've got minus 7 times 2 squared. Oh, 2 squared is 4 times minus 7. That's going to be minus 28. Here's another minus 16 here, plus 12 here. Oh my goodness, I hope this works out. Now, check this out. Okay, perfect. Here's the minus 16 and a positive 16. They cancel out. Watch this. Minus 28 and positive 16 is going to give you, when you add them out, that's going to give you minus 12. Minus 12 plus 12, oh my goodness, I found another factor. Oh, that's so cool. Now, watch what I'm going to do here. I know that 2 gives me a 0. Okay, that's my remainder theorem. Check out the factor theorem. That means x equals to 2. Bring the 2 over. X minus 2 is now a factor. I just found out 2 factors. Look at that. By using this idea of the integral 0 theorem. Checking out the factors on this number. Okay, so guess what? I'm going to take this guy right here and I'm going to divide them one more time using synthetic division. And remember, when I use synthetic division, it has to be x equals to. I don't use a factor, I use x equals to. Okay, so let's go. I'm going to go to this guy. I'm going to put down my factor of 2. Check this out. 1, 3, minus 4, minus 12. That better give us a 0, we hope. Okay, here we go. 1 times 2, 2. That's 5. 5 times 2, 10. 10 and minus 4 is going to be 6. 6 times 2 is going to be 12. 12 and minus 12, yes! Yes! So look at this. Now this is the 1's position, x squared position. So if you think about it so far, what do I have? I have this factor, x minus 1. I found out this factor right here of x minus 2. Oh, look how beautiful this is. And then my resulting one is x squared plus 5x plus 6. Oh, this is getting good. This is getting good. Now I can use just simple trinomial factoring, PSA, to figure out my product being 6, my sum being 5. I know the numbers. 2 times 3. And guess what? That'll be 2 plus 3. So my answer is, of course, 2 and 3. So check this out. This gives me factors of x plus 2 and x plus 3. Knowing these two factors, which I determined from that integral zero theorem, from remainder theorem, from factor theorem. Look at the 3 theorems that I used to figure out that one of the factors is x minus 1, the other factor is x minus 2, and look what I have as an answer. There is that original polynomial that is x to the 4 something or other, right? All factored into beautiful binomials for you. Now, check out what this means, though, later on when we let this equal to 0. I'm going to wait for another podcast, and then I'm going to show you what happens when that happens. Oh, my God, yeah. So many exciting things coming up. This is just great.